So decisions 3 and 4 in the project are sort of the big decisions for the project, which are how do we set the quantity and price for our product that we're marketing in a way that's going to maximize the profit that we make out of this. And when we decide what the quantity that we want is that's going to maximize profit, also we want the full rundown of what that's going to mean to the financials of your product. So what is the unit sales price going to be? How much total revenue do you expect to make in the market? How much total cost is it going to take to produce this quantity of product? Also report out on the marginals of those. What's the marginal revenue and the marginal cost at that quantity? And then, of course, the thing that every executive is going to want to know, what's the bottom line? If we're actually maximizing profit, how much profit do we end up making? So that's the full picture of everything at the end of Decision Report 4 that you need to have come out with. So in our last class, we introduced the concept of derivatives, which is calculus proper. And we did it by talking about marginal functions, using marginal functions as our motivation. So the why behind what we were doing is, say I have a function like my revenue function, which I've graphed over here, quantity on the x-axis, total sales revenue on the y-axis. These functions tend to be inverse U-shaped, right? Upside down U-shaped. If we make no product, then we make no revenue. If we make too much product, then we can't get rid of all of it without giving it away. And so revenue tends to be this upside down U-shaped graph. And we want to know, if I pick a quantity, what is the slope of the revenue graph? That's going to tell me how sensitive, how my revenue quantity changes if I change the quantity that I produce by a little bit. The slope of that green line, called the tangent line to the graph, is going to tell me that. We call that quantity the marginal revenue at the quantity Q. And marginal revenue we're going to use in this course as a synonym for the derivative of the revenue function. So what that does for us, what the derivative does for us, is it tells us not about the value of a function, but how that function is changing. It tells us whether or not a function is increasing or decreasing by giving us either a positive or a negative value for the derivative. And perhaps more importantly today, for the decisions that you're making, the derivative also tells us when a function is neither increasing nor decreasing, because its derivative will be neither positive nor negative. And in most nice situations, that means it will be 0. So if we're looking for the top of the hill, a local maximum value, for example, for a function, we first want to look for points at which the derivative of that function is equal to 0. So the derivative tells us a lot of different things. It tells us the rate of change of a function is an instantaneous rate of change. We think of it like a rate of change at a single point. Rather than taking two different points on this graph and finding the rate of change between two different points, we're somehow quantifying the rate of change at a single point. If we had more time this semester, we would go more deeper into the calculus idea of limits, the kind of powers how instantaneous change works. But in the interest of our time, we're going to leave it at that. Derivative also tells us the slope of a tangent line drawn to the graph of a function. We call it a tangent line when it just barely touches the graph of the function at a single point and is otherwise in the same direction as the graph of the function at that point. So slope of a tangent line is the graphical interpretation for what the derivative tells us. And perhaps most importantly, the derivative of a function is itself a new function. Right? Derivative is almost like a process that I can use to take one function and turn it into another function which measures the rate of change of f, the slope of tangent lines to f, from one point to another. And because the derivative is itself a new function, I can use algebra with that new function to answer the question, where is my f neither increasing nor decreasing? Where is the top of the hill or the bottom of the valley for the graph of f? I can find that by using algebra to find the places where the derivative is equal to 0. So I want to search, if I'm looking for the maximum or minimum of a function, I want to search first for those places where its derivative is equal to 0. We call those the critical points of a function. And so the key algebra step in finding critical points, maximum, minimum points, is identifying the derivative function, setting it equal to 0, so that we're finding places where the function is neither increasing nor decreasing, and then using algebra to hopefully solve that equation for x. So that's what it is. How do we do it? How do we actually find these derivative functions? If I know a formula for f of x, how do I find a formula for the derivative f prime of x? And here the answer is a little complicated because different formulas, different types of function models have different rules for how we take their derivatives. For functions that are powers of x, so x to the power n, where n is a constant, x is the variable, we can take the derivative, as you hopefully just did on today's exam, by first multiplying by the exponent and then decreasing that exponent by 1. So that's what we often call the power rule for taking derivatives. we haven't done much with this, and we probably won't, but I wanted to include it for completeness. If my function is not a power function but an exponential function instead. In other words, if the variable is upstairs in an exponent instead of down in the base, it's a whole separate type of function model and has a whole separate rule for taking its derivative. So the question of which one of these techniques to use depends on where we find our variable x, whether it's in the base, for which we use the power rule, or whether it's in an exponent, for which we're going to use this rule. And the function which has a base of e, the natural number 2.718 and so on, and in the exponent r times x, where r is a constant, we can take that derivative just by bringing down the r, bringing down the coefficient of x, just multiplying by that coefficient. So two separate rules for two different types of functions that we might take the derivative of for the semester. Now, in the project, we don't use any exponential function models. So as far as the project goes, all of your functions, revenue, cost, profit, et cetera, demand, that power the project are power functions. So the power rule is going to be exhaustive for us. Today's goal in your project teams is to maximize profit. Figure out, based on the data that you have in your teams, the revenue function, the demand function, the revenue function, the cost function that you have in your project data. How do we find the point that maximizes profit? And so just to walk back through an example that was part of quiz 2. So that means if you haven't done quiz 2 yet, it's going to be too late after I finish this example. Let's take a look at what profit maximization looks like. If I have this revenue function, so let's say that this is the function that I got out of my regression, and maybe this total cost function. So here's a graph of those two functions. The revenue function graphed in purple, the cost function graphed in green. One of the questions on the quiz, actually it might have been a previous quiz, it was quiz 1, asked about break-even points, the places where we don't make any profit at all, where our revenue, our sales revenue is the same as our costs. We make exactly as much money by selling the product as it cost us to produce the product. At that point, our profit is equal to 0. We call those break-even points. So on the graph, those would be the places where the revenue and the cost are equal to one another. So approximately on this graph, it looks like at a quantity of a little bit more than, what are my units down here? 2, a little bit more than 2, and a quantity of a little bit less than 10, maybe those are in thousands of units. Those would be my break-evens for this point, where the revenue and the cost are equal. At those places where my revenue is below my cost, I'm paying more money to produce my product than I'm getting by selling my product. And that's bad, because that means that not only am I not turning a profit, I'm taking a loss on that product. When the costs are greater than the revenues, then we're in a region of loss. So that's going to happen if I produce less than this break-even amount, or if I produce more than this break-even amount. So the amount of quantity that I should produce for my product in order to make a positive profit is going to be in between these two break-even points, in between approximately 2 and approximately 10,000 units of production. Those are going to be the places where we're in the black, where the revenue is greater than the cost. We make more money by selling the product than we had to spend to produce the product. And profit, by definition, quantifies that difference, the amount by which our sales revenue exceeds our total cost. That's the amount that we call a profit. And if I want to measure that excess, the excess revenue over my cost, it's a process of subtraction. Profit is nothing more than revenue minus cost. And if there's only one thing that you take out of any applied mathematics course for business, it should be that. That profit is, by definition, revenue minus cost. And our goal is not to maximize revenue, and it's not to maximize cost, surely. But our goal in the project is to maximize profit. And so the big question that you're answering with your teams is not where does revenue reach its top, but where does profit, the difference between revenue and cost, reach its top. We can find a formula for the profit function, therefore, by subtracting the revenue function minus the cost function. This is something that you also just did on today's exam. That would give me an equation for total profit. Then we can ask the question, where is this total profit function the largest? In other words, where is the difference between revenue and cost as large as possible? So is there another place on this graph besides the one I've highlighted here where the distance, if you like, the vertical distance between these two graphs is larger than the one that I've labeled here? So where is there the largest gap in between revenue and cost? That's going to be the place where the profit is maximized. So today, with your teams, your goal is to use the marginal revenue and marginal cost functions to maximize your profit. If we were to plot the profit function itself on the same axes as my revenue in purple and my cost in green, here's my profit function in orange, and I'm going to maximize profit at the place which is the maximum point of my profit function. That would be right here on my graph. So my question is, what's happening at that point? Well, at that point, where I maximize the profit on my graph, that point is going to be a critical point of the profit function. In other words, if I draw in the tangent line to the profit function at that point, that tangent line is going to be horizontal. So the slope of that tangent line is going to be equal to 0. So one of the ways to maximize profit is to find the marginal profit function, the derivative of the profit function, and set that derivative equal to 0, and then solve for that quantity. If I do that for my profit function, I just need the power rule to find the derivative of minus q to the third plus 12q squared minus 21q minus 5. Because of the linearity theorem for derivatives, we can do that one term at a time. Q to the third power becomes, multiplied by the 3, decrease the 3 by 1, we end up with minus 3q squared. For 12q squared, multiplied by the 2, decrease the 2 by 1, we get 24q to the first power. There's a secret 1 up here in the exponent that we don't have to write. 21q, well, there's a secret 1 right here as an exponent on my q, so I'll multiply by that 1, then decrease the exponent by 1, I'll get q to the power 0. But q to the power 0 is just 1. And so that q turns into an invisible multiplication by 1 in the derivative. And then last but not least, what's going to happen to this negative 5? Yeah, that's going to go away. This is a constant. This term down here doesn't depend on q at all. And so if q changes, this value doesn't change. And so its rate of change with respect to q is 0, and so it goes away. Derivative of any constant is equal to 0. So there's my derivative function. I can therefore find this maximum point by finding where is this derivative, the marginal profit, equal to 0. So I'll set that equal to 0 and try to solve it for q. I can do that by dividing both sides by negative 3. That gives me kind of a nice quadratic with a leading coefficient of 1 to work with. This particular quadratic happens to factor. Q minus 1 times q minus 7. And because it factors, I can split that factorization across into two equations. One of them tells me that q is going to equal 1. The other tells me q equals 7. And what you'll notice is that q equals 1 on this graph is also a place where the tangent line to the profit function is horizontal. Q equals 7 is the other. And so a valid question to ask is, how do I know which one of these is actually a minimum and which one is actually a maximum? Here we have a graph that reassures me that 7 is actually the max and 1 is actually a min. But if we didn't know that, what could we do to figure that out? Well, what we could do is we could use what's sometimes called the first derivative test and just ask, where is the first derivative, p prime, the marginal profit, where is it negative and where is it positive? Well, at 0, for example, p prime, if I plug in a 0 for q, turns out to be a negative number. So p prime is negative for numbers that are less than 1 for q. Meanwhile, for numbers q between 1 and 7, if I pick q equals 2, for example, and plug it into this marginal profit function, I get a positive quantity. In other words, p prime is positive because p is increasing between 1 and 7. And then for those values of q that are greater than 7, again, plug in something like 10 into this marginal profit equation, we're going to get a negative answer. And so p prime is negative for numbers that are greater than 7. And then using our correspondence that tells us what the relationship of a function to its derivative is, a negative value for the derivative tells me the function is decreasing. A positive value for the derivative tells me the function is increasing. And so this creates what's sometimes called a sign chart for the profit function. Because we know where the derivative is negative, then positive, then negative, we have found where the function is decreasing, followed by increasing, followed by decreasing. And that tells me, therefore, that this critical point at 1, because the function is decreasing on the left side and increasing on the right side, must have been a local minimum. And the critical point at 7, because the function is increasing on the left and decreasing on the right, must have been a local max. And therefore, we've found the maximum profit by setting the derivative of the profit function equal to 0. That gives me my two critical points, 1 and 7 for quantity. And then just using a sign chart to figure out which one of those is a minimum and which one is a maximum. But this equation, p prime of q equals 0, is not the one that everyone always uses to maximize profit. There's another equation that's relatively popular to use in this context. And what it will let us do is relate this not to profit, but relate it back to revenue and cost themselves. So here's an alternative idea. Because by definition, profit is revenue minus cost, and because the derivative is linear by the linearity theorem, P prime is the same thing as R minus C prime, the derivative of the difference of revenue and cost, and linearity says that's the same thing as the difference between the derivatives, R prime minus C prime. So that's the same as the marginal revenue minus the marginal cost. That's what we mean by marginal profit. And so if that's equal to 0, then I can add marginal cost to both sides of this equation and get a new equation, marginal revenue equals marginal cost. So we can maximize profit in one of two completely equivalent ways. We can either find the marginal profit function, P prime, and set that equal to 0, or we can find the marginal revenue and marginal cost functions and set those equal to one another. Either one of those is totally equivalent, means the same thing, and so either one of them is going to find these critical points of the profit function for you. And just to put some meaning onto this second equation, let's think about what's happening to the revenue and the cost functions at this point, production of 7,000 units in this example, that's maximizing my profit. So when my profit is maximized, the marginal revenue equals the marginal cost. That means that if I decided to produce one more unit of my product, just a little bit more product, I would make an additional amount of revenue from that product, but I would also have to pay a certain additional amount of cost to produce that product, and that those costs, those dollar figures, are equal to one another. So if I'm maximizing profit, it means that if I produce just one more unit, it's going to cost me exactly as much to make as I'm going to get by selling it. And so at that point, it doesn't make sense for me to increase my production because I'm not going to get any extra profit out of it. It also doesn't make sense for me to decrease because the amount that I would save in costs, I would lose in revenue. So when I'm optimizing, maximizing my profit, marginal revenue and marginal cost are equal to one another. On a graph, that means that the slope of the revenue graph, that would be the slope of this purple tangent line here at my optimum point, and the slope of my cost graph, that's the slope of this green line here at my optimum point, that those slopes are the same. So what we notice on the revenue and the cost graphs when we're optimizing profit is that the tangent lines to those graphs have the same slope. What does it mean when two lines have the same slope? They're parallel lines, right? So that's on a graph then how we can recognize this optimum profit, is that that's the point at which the revenue graph and the cost graph are parallel one to another.